Thank you everyone for looking forward to hearing this conversation. So I'll first like to introduce my co-founder Rakhee, who will talk about the windows that we worked upon. Basically, she'll run through the machine learning pipelines that we had to do to detect different kind of smells. And then I'll take over from there to talk a little bit about the hardware, what we did, how did we collect the data, and things along those lines. So that's what would be the presentation. We'll be happy to answer any questions if you have. Please feel free to stop us where you feel like, and we'll try to answer those questions out there. So before, with further ado, I'd like to introduce Rakhee. She'll go from here.
Hi everyone.
Hello.
Yeah. So basically, I am the co-founder, as Arpit has said, Actionable Analytics. We developed a machine learning platform, and this is one of the use case of our platform. So as Arpit has told you that he will be taking care of hardware part of things, I'll be running through your software, like how we ran the machine learning pipelines. So when we talk about machine learning pipelines, everybody just talks about what algo you'll be using and how you run, how you select the algo. But when we started, experimenting with different things, we realized this is not just about algos. There are much more to this. So for that purpose, we developed this pipeline. So yeah. So this is what we'll be discussing today: data description and understanding. Firstly, we have to understand the data. Then we have to run through pre-processing and cleaning. I'll be discussing more in detail about it. Then classification algorithms, what algorithms you should be using, how you should be selecting your algorithms. Then results and evaluations. So first is data understanding. So let me just give you a brief background how what kind of data we were dealing with and how we arrived at a solution. So this was like as we have mentioned that it was a e-notes platform. So through this we tried to predict the various orders, right? So to begin with, we started with raspberry, tangerine, and grape. So we gathered all the data through the hardware, and the kind of data we had. So it was not just a vector; it was a matrix. So every data point was a matrix. So as you can see, there were like 11 columns to that one data point. That was one. First one was timestamp. Then there were 8 sensors which were there in the hardware, and every sensor was collecting one reading, right? So there were 8 sensors, then one temperature and humidity, right? Then all the data points, they were stored in CSV file, and there was timestamps on that. As I mentioned, the first one was timestamp. Then there was a valid data points because as they were collecting the readings, so these were the valid data points which we have to consider. I'll tell you why we consider only 2,000 to 5,000 milliseconds. So this is how we have plotted. So if you can see these all different lines, they are all S1, S2, S3. They all are 8 sensors. This is how we have collected the readings, and that's how they will go through. Right?
What specific type of sensors are they?
So they were Figaro sensors. So we'll discuss more about them in detail on hardware.
I'll take that question. So as you can see here, so basically this is the time series. As you can see, that's the time 0 towards your left hand side x-axis, and this is the time in milliseconds actually. So what happens is every time you try to take a reading, one reading is like almost 65 seconds, and during those 65 seconds, what you see in the graph are the impedance, change in impedance, as electrical property, right? So each of these sensors, actually these sensors S1 to S8, are nothing but these are chemi-resistive sensor array of 8 sensors, and each sensor responds to different odors differently. Their impedance changes as they start reacting with the odor. So as Rakhee initially pointed out, we started with 3 fruits: raspberry, tangerine, and grape. And basically 2,000 to 5,000 millisecond is the most interesting part, because that's where we start seeing those curves. You should see pretty much everything else. So basically you see the rise in impedance from 2,000 to 5,000, and then the 5,000 is it goes down, tapers down. So that's what we are trying to capture. So each of these different smells have different kind of a fingerprint, and that's what we try to show up in the next. Yeah, go ahead.
This temperature and humidity is the room temperature?
So basically this is the temperature of the enclosure of the hardware that we have. So I'll talk a little bit about the hardware a little bit later. We'll just go through the pipelines and all, and then I'll come to the hardware, what were the things inside it and things like that. So this one is more about how did we interpret the data, how did we apply machine learning to detect what smell it was. Later on I'll go with the hardware and the things that we used to do that. We did also have temperature, humidity and pressure as well. It's not recorded in this thing, but this is something that we did in the next iteration in the startup that we were trying to get out of Montreal, Canada. This was done 2015-16 time frame out of Montreal, Canada. So that's where we built the startup.
Yeah, so these are the fingerprints which like raspberry, grape and tangerine. They will give you a different picture altogether. And this is how we'll identify the whatever the readings which will give us this fingerprint will be closer to raspberry, which will give to this kind of a pink fingerprint. It will be a grape. So this is all based on the sensor readings which were taken. Yeah.
Did you use one grape or did you use a bunch to average out?
Yeah, we had a bunch of things.
So does the fingerprint change depending on the grape that you pick? Does it vary from grape to
Yeah,
grape
so we
or-
started with essence. So that was, this is the first iteration.
So
Or probably in case we change a little bit, then it will be closer to that, right? The fingerprint which we have created. Can you go back to that slide? They were totally different, right? If you look at this kind of, this fingerprint, it's totally different from it, right?
correct.
So if we get a different, like we tested different kind of essences of like grape, then they'll be closer to it. Not very much diverse.
So,
Yeah.
just a quick point here. So as you can see, like raspberry grape are kind of similar, right? Not very different. So basically, this is nothing but the fingerprint of the data that we have collected. The idea is in machine learning, it's not magic, right? If the fingerprints are very kind of close to each other, then there is chances of a false positive. So basically, when you put tangerine, it will say grape. When you put grape, it will say tangerine. So the idea was how do we separate the smells really well, applying machine learning algorithms. That's what she will focus on, and then I'll focus more on the hardware. How did we collect the data and what were the setup and things like that.
So now comes once we understood the data that this is kind of a data which we are dealing with, it is a matrix, not a vector. So now the problem came in like, okay, we have to do the pre-processing part of things, right? We cannot just jump on to the machine learning algorithm. So we have to undergo several processes under pre-processing. So firstly, we transform the data. So in this case, we have to apply some formulas so that we get the, so as to prepare it for machine learning algorithm. So this is like first thing which we did. We converted the recording digital voltage. The data was in digital voltage, and we converted that into change in resistance. So this whole experiment or this use case was based on a paper which was written by NASA. So we were working on that. So this was the first prototype which we worked on. So then the second transformation which we tried is averaging and summing. Since it was a matrix, we have to convert it into a vector because no algorithm will run on a matrix. So we tried to do summing and averaging. Then because in summing and averaging we were losing the data. As you can see, you'll just be adding so many figures and we'll be writing just one figure. So we thought, since it's like an image, right, as you saw the fingerprints, and we don't want to lose the data because it's so close, like tangerine and grape were so close as Arpit has mentioned. So we try to take the picture in entirety, so we try to apply row and column measurement. So what here we'll be doing, we will be converting the entire row measure conversion, ABCD, like it's a matrix, and we'll be converting that into a vector, so that we would not be losing any data on that.
Just a quick point here. So this is just for the illustration purpose. Our matrix was 11 by 6500 points, right? So there were 11 columns and 6500 rows. So this is how we kind of converted it to a vector. So we could have either used a row measure or column measure. It retains all the data points. It doesn't matter. It's just converting a two-dimensional to a single-dimensional domain.
Then this was FFT, which we tried because this is a DFT kind of a sequence, and we have to, and it was like a time series, so we tried this pre-processing filter. Then we ran PCA. So we tried to do the feature extraction part once pre-processing was done, and here we run PCA, which will extract all the components or features which will impact highly on our results.
So essentially, so the first part was pre-processing, essentially extracting the information from a matrix, converting it to a vector. The second part is actually now started applying like which are the principal components or what are the more important features in this data, so that we can apply it to machine learning and get the results that. Those are the things she is going to kind of go through. So we tried out PCA, which
Yeah.
do other kind of things.
Then after once we ran PCA, then came the data cleaning part, because we have to remove the outliers. As I have mentioned, we have only considered like 2,000 to 5,000 millisecond readings because there the curve was higher and the other part of things were not actually impacting our results. So we have to identify what are the outliers and how we have to remove them.
We can. So this was one of the startups that we had built, but we had applications in fintech. This was our application in IoT, and that's why we are presenting it here. But what we have found out that when we get data, it always is not immediately available to be applied to machine learning. You have to go through all transformation, cleansing, etc. And that's what is illustrated here in our case as well. As pointed out earlier, since we were working with like scientific equipments, we found out that the data that is within 200 to 2000 to 5000 millisecond range is the most important data that is relevant to us, and we would ignore all the other kind of things. Same way we did outlier detection as well and remove those outliers as well. It will kind of corrupt our data to really figure out what the order is.
Now comes the classification part. So we tried different classification algorithms. So here's the illustration, like whatever, like it's a list. So we used Rakhee and Azure ML at that point in time, as Arpit has told you, that it was way back in 2015. So we used open libraries, and that point in time, they were the only libraries which were available. But right now, there are so many companies, like every company is providing the open base. So Python also has libraries, then TensorFlow has it. Now Amazon also has open libraries, so which can be used.
And finally, we compared it with the platform that we had built. So we built Actionable Analytics, which was a SaaS-based machine learning platform. And after comparing with them, finally we chose our platform because it was giving us the best results actually. And so we, as a part of the confirmation, we did compare it with these. So Vector is open source, openly available, and Azure is from Microsoft. They just launched up in 2015. We also tried, since I used to work for Amazon before that, I actually launched the Amazon machine learning. So we also tried with that as well. So in this presentation, we did show that we did compare it with an open source Vector. We also compared it with the publicly available Microsoft, but finally chose what we had built at Actionable Analytics. We call it as Decision as a Service. That's the essential platform we use for machine learning pipelines. She'll go through like how we run those pipelines.
So when we have to classify, like we have to run the algorithms, you have to split the data. First would be like training data set, and then the second one would be validation. So basically, there could be different ways you can do it. So we did like 70s to 30 randomized split. So what we did is we like break our data into 10 data sets, and then we picked up like 70% randomly at one point in time for training purposes and 30% for validation purposes. So that's how we did. Then we used SVM, multi-class neural networks, because can you just why we use that? Because it is very helpful in pattern recognition. So you have to see like whatever algorithms you are using, you have to understand that like we have a frequency. We have a frequency. It was it was time sensitive data, and it has got a pattern. So that's how we actually selected our algorithms. So now this is one of the other like incident tree, KNN, and this lot of other things. Then comes once you have applied the algorithm and you see that you are getting the best result, like if you started achieving 90% of the result from a yeah. you can try and optimize those classifiers, whatever algorithms are there. So there are a lot of ways you can do that. So there are, it's like kernels and stuff like that. So many libraries are available nowadays. Then now, let's just give you a brief process flow, what we have done till now. So data conversion and cleaning. And then transformation like FFT, here we have applied. Then feature extraction and reduction. Cleaning the data. And classification and evaluation. This is how the entire process was done. So this was, yeah. And how we'll measure our results, where we are getting the best results. So there was true positive, true negative, false positive, false negatives, and we have to understand how. So yeah, matrices applicable, accuracy, precision, recall, F-score. So all these are the parameters on which you'll assess whether your pipeline is good or bad, how. So I can just show you few.
Let's see. We'll try to see if we can show it.
Yeah. So here I'll just try to see how, show you how the various, pipelines will run, and we tried different permutation and combination, and we got like, so before starting this process, we were around like 50 to 60% of accuracy, but when we started doing all the, applying all different kind of techniques and, underwent this process, then we could achieve up to 95, 96% of accuracy. So I think it's taking too long. So I think, so any questions, I'm happy to take.
Is your paper available for us to view on Google Docs or something?
Sorry, which paper?
Yeah. The results that you're showing, are we able to view these?
Yeah, I was just trying, but I think it's open on the it's not like, it's taking really longer. Yeah.
So each of your data sets was
Yeah.
based on specific sample sizes.
Yeah.
And so did you do that sampling multiple times, and did you find any variations in the data sets when you use larger sample size with smaller sample size?
So actually the trick is that you have to do a lot of experimentation, like you have to deal with larger data sets or data points, because at times, like if you are dealing just by smaller data sets, then you might not be able to consider the variety or changes and whatever. So it's always advisable to take like
I would even
more
think
and
that
more,
the
yeah.
moisture content of
Yeah,
your
yeah.
sample size would vary, would
Yeah.
make your data vary
yes,
as well.
yes, it will be rich and you will be able to make predictions better. So this is this is the pipeline.
Why did you particularly single out fruit smells? Is it something to do with the characteristics of the sensors you're using, or what were your
No.
criteria for?
Yeah. So to begin with, we started with these 3 fruits, but we, then in the next step we went ahead with different smell of beers, and with vegetables also, and flower, like smell of flowers. So yeah, this was just the beginning, but it was not the end. Yes.
Yeah, no, that was my question. What's the application there? First, business. What's the opportunities?
Yeah, so there are a lot of smart devices which are coming up. So there are refrigerators, like we were just trying to create a chip where we can use in the refrigerator, and they'll be able to say if your things are becoming like rotten and
that's
all,
a good
then,
application.
yeah. So
Very
that is
good.
one of them thing. And in the industry level, just a second. So at the industry level, like there are various chemicals, like various dangerous carbon monoxide or something like that. It start coming up and people don't know. So that ways it is also a good application in industrial setting. Yes. Sorry.
So where do you, so how is the data measured? You put the fruits on a device of that?
So we had a hardware. So we have a hardware. Arpit would be taking up that thing. Like he'll be discussing the entire hardware, how it was. So basically, you want to talk about the functioning
So
of
if
the.
you have 100 raspberries, you're going to measure the time series data for those 100 raspberries. keeping on those hardware?
Yeah. So we started, as I have mentioned, we started with the essence of the food, like with the raspberry, the essence.
So you're talking about like essential oils or?
Kind
you
of.
say the essence?
Yeah.
Essential oils?
Yeah,
Yeah.
yeah.
Okay, that are,
Yeah.
yeah.
Yes.
So for aromatherapy and those kind
Yes,
of things,
yes.
where they're
Yeah.
pretty high quality and
Mm-hmm.
Yeah.
Yes.
so you don't have
Yes.
variation.
They are alone concept.
Do the Figaro sensors lend themselves to particular categories of sense, or can they be used across a wide spectrum of different sense?
Yeah, so they can be used.
Yes.
But this is-
So essentially, this was so I think what we were trying to do was NASA had come out with this concept actually, and they fitted with these sensors in the aircraft, so the rocket that they used to send to the space stations to detect any kind of poisonous gases or any kind of harmful chemicals, so that none of the astronauts should die in the space, right? So we took that technology from NASA and tried to see can we commercialize that at a more kind of a wider level, both in the consumer applications as well as industrial applications. And their concept was that while traditional chemical sensors were based on specific, so something will be very good at, let's say, hydrogen, something will be very good at sulfuric acid, something will be very good at carbon monoxide. But this was specifically focused on chemi-resistant sensor array. That means each of the sensors are individually not sensitive to anything. But if you combine them in an array, they will give you a signature that we depicted earlier, right? So we were taking advantage of array of sensors which are not sensitive to any specific molecular element. And using the the array of all the sensors, we were trying to apply machine learning to detect what element it is. So we were able to apply it to fruits, vegetables, smells, etc.
Yeah, you mentioned an array, you were showing data for 8 sensors.
Yes.
Is that the array?
Yeah, that's the array. So these were the 8 sensors. So we tried with 16, 32. Like our idea was to keep adding the, keep increasing that array.
How expensive are these sensors?
So we were supposed to get the actual array from NASA, but as you can tell, it's a government or federal organization. It took us like almost 1.5 years just to get, give us that thing. Finally, we had to build our own thing. So we contracted with a lab in essentially Concordia University out of Montreal. Just to prepare the first prototype, it was taking us about $1,000 just to do it. But as you can imagine, it's like super expensive. But this is like more like proving the concept, so that we can further get further funding to continue the project and integrate with. So we did get 2 integrations with Fujitsu and Bosch. They became very interested in, so Fujitsu became very interested in detecting different kind of chemicals in industrial setup, and Bosch became very interested in, as Rakhee was pointing out, like in their microwaves, industrial microwaves, intelligent refrigerators should detect different kind of smells to tell whether their food is rotting or is it fresh, is it not. So that was the main idea, and maybe Rakhee can walk through this, like these pipelines. These are the real crux, like when you get the data, how do you tell your sensors are really working fine or not, applying machine learning. So these are some of the pipelines we ran on different algorithms, if you can walk.
Yeah, so somebody asked me about the pipeline. So this is how the platform which we use, then the pre-processing part, all those things like value of data point, whether it's voltage or change in resistance, then the dimensionality reduction, feature extraction, transformation techniques, whether we have used any or none, and then algorithms which we ran, then accuracy, how much accuracy we could derive. So we have listed on like top, I think 7. You can see it's almost like in 90. It's 95%, more than 95%. So we could actually, yeah.
So,
Yes, sir.
A question. So you are mentioning in the beginning of your idea, you want to create a device to tell whether the fruit is still. In the beginning, you want to create a device to tell whether the fruit in the fridge is still fresh.
Yeah, yeah.
So during the measurement, when the fruit is deteriorating, do you see a significant change in terms of your measure results? So like, would you be finding, the rotten tomato actually smells like
Yeah.
banana?
Yeah, so as like even a human nose, if you can smell a fresh banana and a rotten banana, you will see there is a differentiation, right? And so we actually witnessed that there was a differentiation a lot, because some contents have increased, which they should have not, because bacteria are working upon it and stuff like that. So yeah, we have seen it.
Have you guys been able to classify the different molecules, like the organic compounds and things like that?
Yeah. So Arpit, would you like to?
What was the question? What was the question?
Oh, I was just asking if you've been able to classify like the actual compounds involved in like fruit decay, for instance. I mean, can you detect like here you got this bacteria growing because of this particular signature?
Right. So let me just talk a little bit about it. So essentially, we are the machine learning guys. We were trying our hand with building a hardware device that would be able to detect different kind of smells. It was, and the use cases we were trying to solve, like we talked about I'll talk about this hardware and all in a little bit here. But what we were trying to do was, we were trying to go with the use cases where we can get the most funding, okay? That was our idea. At the end of the day, these are like expensive experiments, and so we got that in Montreal. So we went there, we set up a team, and initially we tried our luck with, like Rakhee was showing tangerine, grape, and what was the third? Raspberry. But grape and raspberry were like very similar. So whenever we would show the experiment to our investors, more often than not, raspberry would show as grape and grape would show as raspberry. So we kicked out raspberry totally and put banana in place of it. And as you can tell, as human being also, you can detect the smell, like it's like very different. So it was a little bit easier for us to demonstrate the experiment. So what I would say is that this was more like a proof of concept, but by applying rigorous machine learning to it and tracking just tons and tons of data, we were able to perfect to get an accuracy of like almost 99%, as you were able to see with different kind of algorithms, right? And we picked out the best ones. So we ran several multiple pipelines of machine learning, apply all those feature extraction, classification, validation, like as you saw in that Excel sheet that we were depicting earlier. We were not in particular interested in whether there is some molecule or not, because we were not trying to evaluate the chemical properties of the substance. What we were trying to see is the electrical properties, like voltage and resistance, is what we were trying to measure, based upon certain different, because each of these fruits are very complex chemicals. CO2 is much easier to detect. Carbon monoxide, it's just CO2. Fruits are like, they have acetones and hydrocarbons, organic compounds, so they are just so complex. So if you do the traditional sensor like chromatograph sensors and the chemical sensor, first of all they come like $10,000, $15,000, and you cannot miniaturize them. They are like such like big devices. So our idea was to disrupt the industry in such a way that tomorrow you should have a sensor in your mobile phone, and if suppose you have diabetes or some kind of hypertension, through your body's pheromones, we should be able to tell you that, okay, visit your doctor or intimate your doctor. So those were the kind of use cases we were trying to solve. Of course, we did not test it on diabetes or hypertension, but we have not reached there yet. But our idea was to apply this technology to multiple fields: defense, security. People are conscious for chocolates and coffee tasting, like you can detect that. We did an experiment with Coke and Pepsi. So we were able to detect, this is Coke, this is Pepsi. We were able to do that.
Did you blindfold the sensor?
Yeah, exactly. So we just put two glasses, one was Coke and one was Pepsi, and we just had take the sense, and it was able to tell, okay, Coke, Pepsi. So our idea was to see its mass application, right? So e-commerce, you have to segregate fruits, vegetables, meat, etc. So it can be used there. You have security applications in airports where you want to detect drugs and contraband items, etc. You can put it there. Then you had applications in essentially like a lot of areas like tea tasting, makeup, oils and fragrances industry. So multiple applications, and healthcare, big area, because human beings like sweat, our pulse rate, we secret pheromones, and we wanted to create a device that can detect anything. And since mobile phones pretty much everyone has, we thought we can miniaturize the device so much that tomorrow it will become a system on chip. It can be embedded into a phone, and Apple will become our customer and they'll license the technology from us, and we'll become multi-billionaires. As you can see, that didn't happen, right? But we learned a lot. This startup didn't go anywhere. It just went down. But we learned a ton. Got to live in Montreal, Canada. Who doesn't want to do that? It was a great time. But the learnings that we got were tremendous. Too much of I learned like electrical engineering, which I had completely forgotten during my bachelor's. We got to know like everyone thinks once you have data, machine learning will just work. It doesn't actually. They're so hard a problem to solve. In a very specific test environment, we were able to get very good results. But even to arrive there, we spent almost 1.5 years in that with 6-7 people spread across Canada, US, India, these three locations. So that was the story. But I'll go with just a brief about the hardware, how the connectivity was, how did the IoT picture come into place, right? That is what this talk is all about. So let me just go back there. So this is the kind of sensor, if you can see. So basically, you have a sample bottle that shows a lemon. So essentially, we had test tubes, essentially which each of them had like a sense of like banana, raspberry, whatever we were trying to test. Then this was a sensor chamber, which you see it had like a processor. We used Arduino board essentially, and we had basically a vacuum chamber which can suck the essence from the test tubes. So basically, and it will happen for about a minute, during which the whole process would happen. So essentially, what we do is we bring the sample bottle. It will suck the essence from the bottle. Basically, the air, not the actual essence, just the air. It will suck it, and then we'll pass in the voltage from the device. It will run those kind of things. The Arduino board will actually start calculating the change in resistance at every, like I said, right, in 65 seconds we were collecting almost 6,500 readings that will get collected, and through a Wi-Fi device. So it will spit that to a server which is on the cloud. So that code was pretty much written on Arduino in C. Python code was used to transfer the data from the actual hardware to the cloud on the server, and everything else that you saw on the machine learning is all Java that we did, right? So that was the kind of setup. Yeah. So these were some of the typical sensors that. Yeah, go ahead.
I don't think I caught why you chose the 8051 protocol.
Oh, this is just for depiction purpose. This is not what we use actually. This is just for depiction purposes. This is the paper that I'm referring to that we kind of leveraged. We used an Arduino board, and this is just for the illustration purposes. We had a cloud-based system, and we used a machine learning-based system to detect the. So this is more kind of a statistical-based system. So this is just for the illustration purpose, that what paper depicted and what we modified from there. We didn't do exactly what they were suggesting us to do. We added our own machine learning process, cloud infrastructure, collect the data. I can share the NASA patent that we were trying to use. I can share that. So these are like one of the questions earlier was, were the sensors specific to certain compounds, etc.? Yes, they were. But these are not NASA sensors. Actually, these are Figaro sensors. Our idea was to get those, since we could not get those sensors from NASA, we had to rely with what we could get offhand, off the shelf. So these were like more kind of, sensitive towards, alcohol, solvents, etc., things like that. So this was the electrical circuit, if anybody is interested in that. So the sensor, the output, we talked about that we were interested in changing resistance by base resistance. That is what we were interested in. But we also tried it with change in voltage by base voltage as well. As you can tell with the Ohm's law, V is equal to IR. So R and V are kind of inversely proportional to each other. So we want to try out with both things, change in resistance, change in voltage. Best results we got were with change in impedance, which is inverse of current. People understand that. So we basically got the best results, as I said. So banana, lemon, and lychee. Lychee, if people understand, it's a fruit which is like white from the inside, very thick flesh, very sweet, and it has a very thick like seed inside it, and it's like that's the lychee. I don't know if you get it here or not, but we are getting it there. The lychee, then lemon and banana. as you can see, their fingerprints are very kind of different. So it was a little bit easier for us to prove that this kind of works. Go ahead. So I'll talk about some of the conditions in which we conducted these tests. So the temperature range was 24 to 28 degrees. That was for the circuit and the equipment that we had built. It had to operate under those conditions, and humidity had to be between 59 to 78%. So as you can see, this is another diagram that kind of gives like a block diagram of how it happened. So we had a suction pump. There was a 4-neck bottle chamber. It can suck different kind of. So basically, question would be that if you only send one bottle, let's say a raspberry or banana, it can of course detect that. That's what you're sending it. But we showed it with that we can have different kind of smells, like 4 different things, and alternatively, if we can send it to banana, etc., it will still detect it. So that's how we proved a proof of concept. So first part is training the model. So basically generate as many values as possible for each of those items. So raspberry, banana, etc. Then place them into the chamber. This is how we collected that data. Turn off the PAMP, note the values, compare the accuracy of each, apply the ML algorithm. So that's the process we kept on running entirely. And these are the results, if you can see on the thing, that how we are able to get. So we took banana, lemon, and lychee, applied a support vector machine, PSVM, neural networks, P neural networks, K nearest neighbor, and PK nearest neighbor. So as you can see, for 40 points, so out of almost there were total 40 samples. As you can see, the bottom row, which is the 5th row in the accuracy column, you can see we got the highest accuracy more towards neural network, PNN, then K nearest neighbor, and PK nearest neighbor. Whereas accuracies in SVM and PSVM were kind of 85% and 75%. So those were some of the. Then what we did was just to prove that as we added more in the mix. So that was 3-level classification, what you saw in the previous screen. Then what we did was we added one more fruit inside it. And just by reading this data, can anyone tell which are the 2 similar fruits here? If you can interpret the data out here.
Lemon and longan?
Sorry?
Is it lemon and longan?
Yeah, because if you see, the fruit which have similar kind of fingerprint, right? Our ability to detect that fruit will be very, very low, because sometimes we can detect the other one versus the first one. So we also proved that if you add several kind of items in the mix and you're trying to detect from one classifier, from the one device, it will become much more harder. So we are better off sticking to, for each device, just try to detect 2 things, either this or that. At best, you can try detecting 3 things. I mean, in theory, you can detect as many things just from the one sensor. Like we had an array of sensors just with one device. But the more alternatives you start adding, the accuracy starts going down. So as you can see, so if you see accuracy of all, that means when all the foods were considered, you can see the total accuracy was 49%, 65. The best accuracy we were able to get was 84% in PK and NN. However, but when we used the fruit banana and lemon, the best accuracy we were able to get 96%, up to 96%. But when we did, lychee and logan, you can see the accuracy fell down below. Why? Because lychee and logan are very similar to each other. So our ability to detect each of them is like very difficult. So those were some of the things that we were able to get, and those are just some of the insights that we were able to draw out of this. So happy to answer any questions. I know it's I think we're about time, but happy to answer any questions. Just go ahead.
So this work is really, really interesting. Are you familiar with the paper by Gerard Lecoq that just came out? He called it synthetic sensors, which he was using a microphone, MEMS sensors, and other things, but largely using your same technique to interpret events around a room.
No, I have not. Since then, I moved on to actually fintech, so we were doing credit scoring and credit modeling, fraud detection. This was done like 2015-16.
Well, he just published it last month.
Oh, really? Okay.
Same basic approach as you're taking.
Yeah.
And it shows the commonality of the ML pipeline.
Yeah.
You might think about how that could apply in other contexts where you have a
Right.
discrete set of various sensors using the same technique.
Right. I think this is a great approach. I think the shortcomings that we kind of the challenge that we really faced was, first of all, Montreal is no Silicon Valley, so you can't get funding as much as you want. We were trying to get like about a 5 million, and the reason was that had it been just software, maybe we would have been okay. Because we spent so much money on the hardware just to try to miniaturize that, NASA was giving us hard time. They were not giving their actual. We thought we will just do the data interpretation and analysis and what, because hardware somebody else will do it for us, and we'll demonstrate its commercial applicability. We had to just go whatever was out there, bring it, make sure it gives some closer results as we could have got from the actual array, sensor array from NASA. And then starting to, so we started with like this big like a box, right? So valve and do those kind of things. Then we made it like half the size of it. Then we had problems with the mechanical, like the sensor, it would not because when you suck in the air of like raspberry, and just after that you put, let's say, banana, there will be some residual air in the chamber. And because of it, it will start giving you the bad results, because even though you have now put banana in the chamber, so we have to have like multiple chamber array. Make sure when you put the next element, you should run a vacuum cycle just to make sure that there is no residual kind of element left inside it. Those were our learnings as we move forward. Another big challenge that we faced was that hardwares are just tough. I mean, we had like electronics guy come in and say, okay, this is not working, that is not working. Then the readings that we used to get, sometimes some of the lines would skip and we would not know like exactly what happened. Then we figured out that the board that we had sometimes used to skip, or the frequency was not good. So out of 6,500 readings, few of the readings would miss. And if those readings were on that curve where the actual curve is important, then it will again cause like erroneous results. So a lot of understanding the data, understanding the hardware, how it operates, then whether the time frequency is being maintained between each of the readings that we are getting. So those were some of the challenges.
You showed 5 sensor types. Did you use all 5 of those?
No, so we actually, this is just for the, so there was another paper written by another professor in Taiwan. Since we could not get the actual sensors from NASA, we were trying to leverage what somebody had already done research in Taiwan, but still went ahead with our own implementation. Their implementation did not include machine learning. Our main forte was that we can actually apply machine learning, because machine learning works really well in fuzzy environments. So it will not give you the exact results, but whenever you have some, here and there things which is within the given controlled set environments, it really works well, which is what we were able to prove by getting 95% accuracy in certain specific, experiments that we ran. So yeah.
So where did it fail? You said that in a controlled environment it was really good. So I imagine you have 1 cent in the chamber, you're good to go. But like in a refrigerator, you got all kinds of smells. Is that?
Yeah. So as we said, like we got some deals with Fujitsu and Bosch in Germany. They ordered our device to test it out. Before they could do anything, our company went down. So I don't know what outcomes they would have derived. This I can say is like more like we were about to be get there, but we couldn't get funding to see the outcome, like what did they do with that device. We did sell 2 devices, one to Fujitsu and one to Bosch. And Fujitsu was from Japan actually, and Bosch from Germany and the US actually. And I was also being told that Google, Apple, Qualcomm and Intel were actually interested in this device. We were not confident that we were there for them to have a look at it. You see what I'm saying? because it was like very rudimentary, right? It was not like the most sexiest thing and all, but we were very happy what we were able to achieve. Maybe we should, now thinking back, maybe we should have shown them something, maybe we would have got some money from them to improve the device or something like that. Yeah, it's 1 year, 2 years ago story. Yeah.
So how long it will take to do the training?
So basically when we have to get one reading, it used to take us about a minute, and then to clean up it would take another minute. So for one reading it was like a minute. So to build a good model, we at least need to take some 100 data points. So it is we are talking about at least 200-300 minutes. So we have to collect data for at least almost like 15-20 days just to build one model. Because the data generation part was so lengthy. So earlier it used to take us like 2-3 months just to create one model because the data generation itself was so slow. So we were even evaluating different kind of simulators that can generate data on the computer. But then we did not know if we simulated on the computer and generate the sample data, will it be anything near to the real thing? So we were not sure about it. So we had to go with the actual data, and it was taking a lot of time. So we reduced it from 3 months to like 15 days to get one model out. So the coding and all those part was easy. Just the data generation part was very difficult. So somebody had to physically go put those tubes there, then process it, then make sure it is running fine, it's not heating up. It was like very, how do I say, it was not very sophisticated like a lab and something like that, right? It was like very rudimentary thing. We were trying to get that thing, like a system on chip, but it was like costing like $1,000 just to keep experimenting on that. A lot of like moving parts were there. If there is one takeaway from it is don't do a hardware startup unless you know your shit really well. Right? Yeah.
Do you think you'll consider another go at this?
I would if I get funding. I would. I've done a lot of stuff here. We both would be very happy. Somebody is our investor here. Please come talk to us. We'll be happy to go with it. Half of the work is already done. Hardware part is what I think we did not figure out really well. Yes, go ahead.
I was just doing some quick research because I had my original degree was in physics. So wondering why you did you choose the electrochemical sensors just because that was the easiest thing to obtain, or did you consider using a variety of different ones? Optical versus simultaneously with.
So basically, the investment that we had got, they had already done a deal with NASA, and the idea was NASA will be providing us those sensors, and with them we move forward with that. So I don't have any background in chemical resistor sensors. I had to read all that stuff. I'm like software, like computer science engineering. But I know enough about electrical, mechanical, enough to put this thing together and do it. And if I did not have to wear different kind of hats, right? Okay, now I'm an electrical engineer, now I'm a mechanical or anything, whatever it takes to get this thing out. So I did that, but the initial basic research was done by NASA. So that's the patent we used, licensed it. And they were the equity holder in the company as well. But they never shared their actual sensors, and we had to go out and keep trying different things.
While you were talking, I was looking up some papers, and they had one that was called a brief survey of gas sensors, and we were talking about it. And I was just curious if you had considered I guess I would call it multispectral or
Yeah, I think the thing that we were trying to do there was those spectrum analyzers that you're talking about. They're so expensive, they're $25,000, $30,000. Our aim was to go in a different route because they are specific to, they analyze the molecule of a chemical and try to detect what kind of properties there. Our approach was very different. We didn't care what molecules that are there. We just cared about the electrical changes in the
You
properties.
wouldn't need a full spectrometer, but you might be able to have something that's targeted to detect different things.
Right. So
Optically.
I think our premises was that since it started with the NASA, and NASA kind of never gave their real hardware to us, so we were like, from the very starting, we were like not, set up to succeed because hardware was so tough for us to do, and none of us were like hardware engineers. So we did the IoT part, the networking part, collecting the data part. We even did like putting together the chip and getting all those things done. But I think we failed really bad on the getting the real system on the chip, and we didn't know what the hell these guys were doing. all we were interested in, can you get me more data? I want to put the machine learning, get those things out. And I think we really screwed up on the hardware. And the problem was we were expecting NASA to give it to us. They never gave it. As a startup co-founders, we did whatever we could do to the best of our abilities. Hired some people who claimed they were hardware experts, which we later came to know they were wrong because it didn't work out. So yeah, those were some of the learnings later. Yeah.
So you are going to commercialize your technology. So to this, you are going to commercialize your technology. So to this end, so
I have also code.
yeah,
I have.
So to this end, so what are you going to do next? So you have.
This is some IP that we created. It is with us. If somebody is interested, we will be more than happy to. We both are co-founders. She ran the complete machine learning, the pipelines as she was demonstrating. I was running the complete engineering, hardware. I mean, I'm not an expert, but after doing this, I know enough about how to put those things together, the IoT stuff and things like that. So this we did in like 2015-16. After that, we got acquired 2016. So basically, we both are co-founders of Actionable Analytics. So it is a SaaS-based machine learning platform purely. This was one of the other startups we started building, applying Actionable Analytics, the machine learning platform that we had built. So that we were doing, in Montreal, Canada, but then we got acquired in 2016. The platform, not this startup, the other one that we had primarily, and we started focusing on fintech. So last 1 year we have been focusing on credit scoring and fraud modeling, risk modeling, that kind of an area, which also is an application of machine learning, but not what I just demonstrated here today. But since this was an IoT meetup, so I can't show credit risk modeling. If you want, I could do that as well, but not for this meetup. So, any questions? Yeah, go ahead.
Here, I would like to add upon it, like as Arpit was mentioning that we get into fintech. So whatever we learned in this entire scenario, the use case which we're doing for IoT company, we have whatever the pipelines we ran and the experimentation. So this is the kind of IP which we have generated and we use for different use cases like fintech. And in fact, we are now working on an insurance tech company also. So we are using this platform and the learnings which we have drawn. So software is like really working and it is successful, but we only failed on hardware part of things.
I think that's a good part. We did build like an insurance tech platform, again leveraging the machine learning that we have done. It's a bootstrap startup. We already do about 200,000 GMV a year, already doing that. But still it's early stages. We do like 20K revenue on that. It's like a platform wherein people can get multiple kind of insurances done. Right now it is only in India, not in the US. But we intend to kind of keep working on that as well. So again, it's not IoT, but it's a separate thing that we are also doing right now. That's all from my side.
So insurance tech also includes IoT because we collect a lot of data in order to determine the premium for health insurance and stuff like that. Like Fitbit, you wear devices or using your phone for collecting the data. So that data has been used to determine how much premium you should be paying. So basically, a healthy person should pay lesser premium than a person who has some kind of disease or something like that.
And same thing goes in the driving premium. So there are devices in the cars which detect how fast you drive the car, how many times you have put the brakes on the car, etc. And that data should determine what's the premium on your car insurance. So our idea is to leverage those kind of information to give you dynamic pricing on what should be your premium policy. That's where we're trying to apply now. So we'll see how it goes. Yeah.
So here, the key is we are not building the hardware. The hardwares are already there. We are just using the data, which is emitted by.
Which is where our expertise lies, I think. Yeah. Any further questions?
So you said that you have failed in the hardware. So does that mean you can't proceed any further on that, or you need to make any more changes?
I think funding was the toughest nut to crack. We tried to bring a lot of investors. Everybody would say, great job, excellent, you're doing this, but I'm not going to invest in it. So we were trying to, earlier we were trying to do like a 5 million, then like 7 then we came to 5, then we said okay 3, we said okay 1 is also good. So we ate up all the $500,000 we had in about a year.
So were you trying to sell the hardware, or were you trying to sell the?
So our idea was trying to license it with more OEMs like Samsung, Fujitsu, because we don't have money to invest in that kind of a research. This is like scientists should be sitting on this for years and coming out with those things. So we were trying to prove a concept that if it is done right, there is a market for it. So we'll rather focus on the cloud analytics, that part, as long as some of these OEMs such as Samsung was we were trying to target Samsung, Qualcomm, who does this chip and all those kind of things. These are not standard chips that are available out in the market, anybody can do it. These are like very specialized things. Our focus would have been on more on the cloud infrastructure, applying machine learning to it. So our idea was, even we who did not know much about this hardware can put something like this together. So if companies who are expert in this areas can definitely take this thing up if we do a proof of concept. So that's what we did. And as I'm telling you, we did sell two devices to Fujitsu and Bosch. I don't know what happened after that. We did that.
It'll come back.
Yeah.
I mean, it has to.
Yeah.
And I see the market there. There's tons of it there.
Yeah, exactly. There are just tons of use cases: security, defense, tea tasting, chocolate tasting, coffee tasting,
agriculture.
Agriculture, horticulture, makeup, fashion industry,
Fragrance lines.
Yeah, fragrance lines. All of them.
Nobody needs a grip.
Exactly. Just tons of opportunity for that.
Exactly.
Thank you.
How a couple of algorithms, machine learning algorithms.
Sorry, what's the question?
So you have tried out a lot of machine
Yes.
learning algorithms.
Yes.
So my question is, those algorithms, the code comes from the NASA, the open source software online?
No. So those algorithms are algorithms. We use our technology. NASA's technology was just the hardware, which they never gave anyway. So this is pretty much ours. Everything is ours. So you can say the initial kind of concept or idea was from NASA, and our idea was, if they can detect different kind of smells in the rocket to protect the astronauts, can we leverage the same hardware and technology to detect different kind of smells? So that was our kind of modification, provided NASA would provide that basic hardware, which they never did. So it's pretty much everything done by us. And they didn't have this concept of machine learning or whatever. We did it ourselves. Thank you everyone.
All right.